Yeah, good afternoon. Can you hear me?
Yes, sir.
Okay, Balaji, you can share and you can start presenting. Okay, I'm recording the meeting already.
Okay,
Okay,
sir.
so
Yeah,
please proceed. Yeah,
yeah. Let me go ahead.
yeah.
Yeah, yeah. So I hope my screen is visible and my audio is clear. So let me start off with today's work. So today I will be conducting a demo for the inverter schematic and layout. So we will be mainly focusing on how to perform the layout for an inverter. Okay. So let me start off. Uh, I have already created a library called INV here, but let me just do it all over again now so that we get everyone on track. I would recommend that you guys do not try to implement it right away because there are a lot of steps you might just miss out if you start doing it side by side. So maybe you could look at the steps now clearly and go offline and try the implementation on your own. Okay. So let me start off. So I'll just create a new library. I'm just calling it demo2. Okay, so let me create a new cell. I'll call it inverter. Okay, so here let me construct an inverter. So last class I think we did not look at uh, sir, am I audible? Is everything fine?
You're audible,
Yes,
sir.
sir.
Yeah, okay, great. Yeah. So last class, I think we did not look at these two symbols, which is, I think we looked at ground, so maybe we did not look at VDD. So VDD and ground are two components which you can find over here. And these guys do not need to be named as specifically VDD and ground. They internally come with the name VDD and ground. So you don't need to export them. Okay. Uh, So I will be constructing a basic inverter, which is nothing but an NMOS, PMOS, connect the gates. Yeah.
Sir, the concentric circles is the VDD, right?
Yes, this is VDD and
Okay.
this is ground.
Okay.
Okay. Mm. Yeah. So I've connected the VDD on top, the ground bottom, and then basically I'll be connecting this node together here. Okay. Uh, and as usual, I will be bringing in the pins, the input and the output pins. And I'll be connecting the input pins to the gate. Sorry. And the output pin to the source. Okay. Uh, Sorry, the drain of the NMOS and the PMOS. So now let me let me export. Control plus E is the shortcut for export. So I'm performing Control plus E. I'm calling this input. So I mean this is the export characteristics is input, and this will be called, let's say, INP. Okay. And again, I will be using Control plus E, and this is of type output, and let's call it OUT. Okay. And you from last time you may remember that we need to export the we need to set the spice model. Just Shift plus S, or you can go here and set spice model, or Shift plus S. So I'll just use Shift plus S. Basically, go and click on this PMOS and just do Shift plus S. You'll obtain this set spice model. Okay, and just make sure that you have this line that's connecting here that basically indicates that this is the PMOS where you're setting the spice model. Okay, so name it PMOS. Okay, and again go to this and click over here. Basically, sometimes if you click here, no, the length and the widths will get selected. That's not what you want to do. You need to click somewhere over here. Okay, and then you do Shift plus S. And now you can see this, just drag this outside and you can see this connecting line. Let's call it NMOS because that's the name given in the model file, right? So now we've constructed this. Let's just go ahead and write the spice code. I already have the spice code for this, so let me just copy it from here. Control plus C and Control plus V works here, so you don't need to worry. And if you click on zoom, right click and drag back will help you zoom back, and right click, drag front will help you zoom in. Zoom in and zoom out are also simple this way. Okay. So I've copied it and Control plus V, I'm going to paste it here. Okay. So now I've pasted the spice code, right? So if you can see, let me just expand this and show you what it is. The spice code is nothing but I'm including the model file in the first line. The second line, I told you before that the VDD and ground pins need not be exported. So you can directly define its voltages right away here. The ground is by default taken as the minimum, which is 0 volts. And VDD can be defined by writing a statement like this, where V1, the first voltage source, is between VDD and ground of DC 0.8 volts. Okay, as discussed before, 0.8 volts is our VDD in this technology. Okay, so V2 is I'm basically giving an input PWL where of this form you will see when I plot it in the output. A PWL is nothing but a waveform where you can define time instants. So like it goes like this. So 0 seconds, the voltage is 0. At 100 picoseconds, the voltage is 0.8 volts. At 1 nanosecond, the voltage is 0.8 volts. And again 1.1 nano, 0 volts, 2 nano, 0 volts. So it's basically time followed by voltage. Time followed by voltage. Okay. I hope this logic is clear. Uh, and the next line is dot tran. So last time we did dot DC. So this is to perform a transient analysis. So when you have inputs which have changing voltages with time, right? You basically you would prefer to perform transient analysis. So you will do dot tran. So dot tran 2.1 nano. So I'm simulating this setup for 2.1 nanoseconds, and that's it. Apply and close. As we know earlier, right spice deck is W plus S. So W plus S. Okay. Now I will add traces, which is V in, not V in and VDD. This guy and V out, sorry. Sorry. In my spice code, I have named it as V in, so I should change it as VINP. Okay. Let me just rerun it. And I'm going to save this JLib anywhere here, and let me call it demo 2. And I'm going to rerun it with W plus S, right? VINP and V out. Yeah, so here is your inverter characteristics. You basically see that for 1, the output is 0, and for 0, the output is 1. Okay, so here we have built a basic inverter, but the aim of this tutorial is to like show you how to build a layout. So, what is a layout? So, let me just create a layout cell, create new cell, and go to layout and call it so keep this as your convention. Okay, so call all your layout cells as the same name as that of your schematic inverter. My schematic is called inverter, so I'm calling my layout also inverter under the library demo 2. Okay, if you do that, you can see that is everybody speaking? Okay, yeah, if you do that, you can see that the layout is appearing over here below inverter as one common thing. So it will appear as a drop-down menu like this. The same. Once you do this, I would suggest that you rename the layout. So in order for it to appear under one single drop-down menu, I've named it as the same name as that of the schematic. But for some future purposes, right, it will be useful to just go and edit this name as rename cell, sorry. So it's supposed to be, you need to go and rename cell as library name, which is demo2 underscore underscore inverter, or the schematic name. Uh, I will tell you in the next tutorial as to why this is done, but just follow this convention. First, name it the same as the schematic, and then go back and change it to the library name underscore underscore schematic name. Okay. So once you have done this, now you've entered what is known as the layout realm. So here, what is a layout? Basically, a layout is nothing but sub silicon level uh, view of the circuit that you have built. So you will actually be giving the foundry a silicon level design and ask them to manufacture this design for you. Okay, so the foundry cannot understand your schematics. Your schematic is nothing but a bunch of NMOSs and PMOSs and all, but the foundry requires you to give them a set of connections where you just have substrates like metals and other things, right? So that is the basic idea of making a layout. So before we get into this, I'll just take some time to explain some of the components here. Just as we did in the schematic, there are some components even in the layout that you need to like understand and get a feel for. So I'll just explain that a bit. Okay, so yes. So yeah, I hope this screen is visible, right? It's the page, it says layout basics and all of these things. So here I have a bunch of basic components that I've listed out here, which may be important to just look at right now and understand what is happening. Okay. So the idea of layout is basically place all the transistors and connections and interconnections as you have in the schematic here in the form of metals and substrates and so on, right? So firstly, let's say I bring out an NMOS. Okay, so I have an NMOS over here. You can see here, just left click it and bring it here and place it over here. Okay. And click on this and to Control J to obtain this view. Okay. So I'll just take a minute to explain what this view means. Okay. So as you can see here, you have an active layer, which is in green, which is this part. Okay. Let me just zoom in so you can see it clearly. So this is your active layer. Okay. Uh, so what is an active layer? I will show you over here, right? So when you want to perform, like let's say when you want to uh, define an NMOS in terms of the layout components. So what it means to say, what it is this. So first you will have a substrate here, which is this. And in our case, the substrate is nothing but everything outside this, whatever you can see here. So this whole thing is a piece of every region outside is a piece of. Okay. Nextly, you have an oxide, but then the oxide is not shown anywhere here. So first of all, before I go further, always remember that the layout is always the top level view of your MOSFETs, right? So when you look at this is the height, let's say P sub and all these things are in the height dimension. But let's say you're looking at it from here. Okay, let's say you're looking at it from top. So this is the view that you would want to like keep, so that this is the view in which you will be constructing your layouts. Okay. So yeah. So having said that, moving further, now this is your P sub, and as told earlier, the whole outside region is your P sub. Secondly, uh, what is your active region, right? So an active region is nothing but you have an oxide layer which is shown here, right? This whole thing is an oxide layer on top of the P sub. Now, when you want to make a hole in the oxide layer and expose the P substrate out for some kind of doping, okay, that's when you will employ the active region, which is nothing but the green part, right? So this green region is the active region, which basically etches out or removes the oxide layer only in this square box within. So all of this region within, right? This whole box, this whole thing is the active region where the oxide is removed. Okay, I mean, what here? Yeah, over here. Okay, so all of this region is where the oxide is removed. Secondly, an N select, right? What does an N select do? When you apply a region called a layer called N select, you tell the foundry that wherever this N select is there, please make an N plus diffusion over there. That is so all of this is nothing but you're giving the foundry an instruction of how you manufacture this NMOS, right? So here, when you say you've given an N select region, you are basically asking the foundry to give you an N plus diffusion. So that is the use of N select, right? So an active region is common for both PMOS and NMOS. As you can see here, it's just this green color thing. But depending on whether you have a P select, this one, or an N select, which is this one, uh, appropriately the required P plus or N plus diffusions are made. Okay.
Sir, so in that active region where the oxide is removed,
Yeah.
this N select or N plus or P plus will be diffused to make that transistor.
Yeah. So basically now you've removed the oxide layer, right? So now there is an external machine that actually puts in this N plus region in that removed portion, which is dictated by this green layer. Wherever you've given this, wherever you've given this yellow color thing, you're asking the machine to basically diffuse an N plus there.
Okay.
Okay. And further, so this whatever you see here, right? This color is polysilicon, and that is over here. And in your layout, it is this guy. Okay, so as I told you, this is the top view, right? So here is the polysilicon which I drew in this fashion, where you will basically look at it from here. Okay. So yeah,
Excuse me, sir.
go on.
So what is this green region, sir? Like with respect to the NMOS?
The
Because the
green
yellow
region
region is
is
the N plus. What is
correct.
the
No, no,
green?
no. See, the green region is nothing but an active region. So what is an active region? So let me just construct this. So firstly, you have a whole. Firstly, you have a big. I mean, imagine it in 3D, right? Like this whole thing. Okay, wait. Let me just draw a trapezoid. Yeah. So this part, if you see, this whole thing is an oxide, which is already there on top of your P sub. Okay. Now what you want to do is remove this oxide region, and for that you draw a layer called N plus. I mean, sorry, you draw a layer called active region, right? So what that does is it basically removes this much of layer and it frees it up, and it opens up the P substrate for you so that you can apply some kind of doping over there. Once you've removed that area, that's when the P sub will get exposed to air, right? So this you can imagine it in 3D, where P sub was initially covered by oxide, but later you just etched the oxide out. Once you do that, this P sub will be open to air, and you can diffuse whatever you want. So here I am choosing to diffuse N plus, which is the yellow layer, the next layer which I'm showing. So when the foundry, I mean, looks at this green layer, he'll first remove the oxide there. And when he looks at the yellow layer, he will etch N plus kind of diffusion over there. That's the idea.
Got it, sir.
Okay. Yeah. So this is just a very quick overview of how the Foundry interprets your layout. I mean, as time goes forward, you will look at various things and various other components, and we'll discuss one by one as and when it comes. Okay. So having said this
Sir,
basic,
sir,
yeah.
sir, as we remove the oxide, the gate will conduct. Is there not a problem?
As you remove the oxide, can you come again? Oh no no. You can
Then,
see you can see here, right? The wherever the polysilicon is, below that there will be oxide. That is not removed. Below the polysilicon, I mean, in my figure, it looks as if this whole thing is removed, but in actuality, this is the polysilicon below which the oxide will not be removed.
okay, sir.
Okay. Yeah. Okay. Having said all of this, this is a very crude and basic introduction to layout. So we will, as layout designers, what we have to do is basically give the Foundry a set of instructions on how to, uh, I mean, what your circuit is actually describing. And the Foundry guys have already given us a set of rules by which we need to follow. Like in the sense, I cannot place two NMOSes. Let's say I just place two NMOSes here and I bring it close. You can see there is this N active spacing is 5.6 or something, right? When I bring it very close, it says error. Can you see this? Okay, so whenever you see an error like this, whenever you're bringing it close and you see an error, that means it cannot move more than that. Okay, so there are some rules like this, and these are called DRCs, design rule checks. These are given by the Foundry to us as designers to follow so that the Foundry doesn't have any problem in taping out whatever design you've given to them. Okay, so the idea of layout is to give a very compact, low area, DRC clean, okay, layout. And also the second thing is LVS. So there are two components in layout. So one is called design rule check, which is given by the Foundry, which basically dictates certain things like just now I showed you how close you can bring two NMOSes together, right? I mean, like this error, and there are so many other errors that the Foundry has defined for you. That is called design rule check. The second thing is layout versus schematic or LVS. Basically, what this check tells you is does your layout accurately describe what your schematic intended to do, right? So in your schematic, this is the thing that you intend to build. You want an NMOS or PMOS, you need this kind of connection and all of that. And in your layout, you need to make sure that that connection has been made. So that is the use of layout versus schematic or LVS. Okay, so these are the two things that you will have to look for in a layout. Okay. Having said all of this, we will just proceed to make the inverter layout now. So I have one NMOS here. Let me pull up one PMOS, which is over here. I'm pulling it up here.
Excuse me,
As,
sir.
Yeah.
This yellow layer, it is beneath the green layer, right?
The yellow layer is a dotted layer on top of this green layer. You can see this. Let me zoom in. Yellow layer is on top of the green layer.
Oh, okay.
Okay. And in the PMOS, you can see this yellow dashed layer is on top of this green layer, this whole thing.
Okay, those two are N select and P select.
Exactly. Okay. For I mean, basically, the names for all of these will appear when you come and place your cursor near here. This is called P active. So when an N select plus diffusion is put together, so let me come to this. Yeah, so when an N select and when the green layer and the yellow layer are put together, the whole thing together is called as an P active or inactive, respectively. Okay, so that's one piece of information you need to know. Okay, so now we know that the PMOS and NMOS is here. What is the next connection that's left to do? You need to basically you need to perform the connections between the drain. Like let's say over here, you need to connect the source of this PMOS to VDD, the source of this NMOS to ground. You need to interconnect these two drains together and pull it out as out, and connect these two gates together and pull it out as in. These are the connections that you need to perform in the layout. Okay, so how will
Sir,
we?
just a minute.
Yeah.
So the yellow layer is the active layer, right? So what is the yellow layer? Outside of the green region, like it's of no use then, right?
Exactly, but see, all of this is so when you say there is an n select, it just tells you perform an n plus. See, all of these other things are given by the foundry itself. Like let's say this whole box, right? I'm just placing it over here. I'm not. In practice, I may have to draw these layers on my own when you go on to like Cadence or other tools. But in electric, you can see that these boxes are already they've come as a package. You don't have any control over this. Okay, so there are some so as I mentioned, right, DRC, there are some design rules as to how much this n select should be above, like, I mean, how much should this n select be more than this active region and all. Like there are these rules that are defined by the foundry, and when you perform DRC, you will get to know these rules.
No, so I meant we dope through the active region, right? So
Yeah,
why do
I
you want to
get,
select
I
region
understand your
outside
point.
the?
You're saying why not place the rectangle region exactly on top of this,
Yeah,
right?
exactly.
Yeah. I understand that, but again, these might be some rules that have just come from the foundry. I don't know if you can change it as of electric is concerned, at least.
Fine. Okay then.
Okay.
This the oxide layer, is it invisible, sir?
Is it?
Invisible, sir. It is
Yeah,
not
the
shown.
oxide layer is not shown in this top level, in this top level view of the layout. It's not shown.
Yeah,
Is it below
Balaji,
the?
you have sorry, Balaji, you have 20 minutes, so you need to accelerate a little bit. Okay.
Yes. Okay,
Yeah,
guys, like I will send out 2 more videos to understand the layout in better detail. Just watch these videos offline and then post your doubts. Okay, I know this might be a little overwhelming, but just watch these other videos. And for this session, I'll just go ahead with how to make the layout. Okay. Yeah. So once you have an NMOS and a PMOS, the next things that you need to perform is connect these. So have PACT here, enact here. So these define your sources and your drains. Huh. PACT for your PMOS and enact for your NMOSs. Okay, so firstly, let's look at, let's maybe go at one thing at a time, maybe just NMOSs only. So now when I want to connect this NMOS with this uh, uh, enact, right? So what I do is I go and I start placing it closer, closer, closer until I see an error. So you can see an error which says error spacing is 2.5. The spacing is 2.5, but the minimum is 3. So you need to ensure that the spacing is 3. Okay. But then sometimes when you actually connect these two guys, so you're supposed to connect this active region to here, and now you actually and try bringing it closer. Actually there's no error now when you bring it closer because the connection has been made. Okay, now you bring it closer and you stop where there it points an error. See here again the spacing is actually 3, but I've gone to 2.5, so that's an error. So just move it left and place it here. So that is your connection of enact. Okay, so you created a source or a drain, whatever you may call it. And next I will again create another connection like this. I'll first connect it and then bring it close. So the spacing is 3, and now I maintained it at 3, so it's all done. Now you can see there's one whole yellow layer that is being, an yellow layer that encircles the whole NMOS, right? So when you bring it little farther away, there is this spacing. You don't need to, the spacing might cause some other DRC violations when you perform DRC. So how do you perform DRC? Tools, go to DRC, check hierarchically. So, or press F5, right? See, you can see that there are 2 DRC errors. So, and how do you look at the errors? You can go to Explorer, Errors, and expand this and see the error. It shows you that there's an error. Okay. And when I bring this closer and perform tools, DRC, check hierarchically, that error vanishes. So let me just delete all. Tools, DRC, check hierarchically. So there is no error now, right? So I would suggest at every step, whenever you make a new change in your layout, just go to tools, DRC, check hierarchically. Every time keep pressing F5 whenever you make any change, so that you don't have to deal with these DRC errors at the end. Okay. So that is your NMOS, and let's make a PMOS now with its drain. And so Control J to rotate it 90 by 90 degree, and make sure that when you place this NMOS and PMOS, right, you don't have these layers being overlapped. If it overlaps, there might be some errors. So just place it right on top like this. Okay. And now connect your PACT and perform the connection like before. So PACT, bring it close. There's an error, but you can connect it. Sorry. So always click on the PMOS first, this part, and then click here. So that, sorry. Yeah. So let me just do that again. So how do you perform this connection, right? So the length of this active region is this much. So let's say you want to maintain the same width or something. So you want to maintain the same width here. What you do is you click on this guy and go next to this guy here near the edge, and then right click. Okay, and there is this connection which is made. But the other way around, you may end up having some larger connections. Like, I mean, like if you do it, this case is not working, but you've seen before, right? Like, yeah, you do this, there is this whole big connection, but let's say you don't want that. Just place it a little farther away like this and connect it like this. Okay, and now bring it close. Just bring it here and bring it close. The distance is 3. Okay, do the same with P act. Okay, and now place all of this slightly above like this. Okay, now you have this spacing, and basically this is nothing but your N well. The dotted black dots are your N well, and this black shades are your P well. Okay, so you can look at that also from my. I will share this document of layout basics, which tells you what each layer means. Okay, so basically this is the N well and this is the P well. Moving further, now the next connection you want to make is this. So you want to, let's say you want to connect the drains together. How do you do that? Click on this guy. Okay. And when you click on it, you can see that you selected metal 1 P active contact. So this is a contact which has P active, the region P active and metal 1. Okay. So you can bring this out like this and you can, I mean, basically click on it. Left click on this guy. Once you see this, just go outside and right click. You can see metal 1 is being dragged out. Okay. Once you do this and go back here and click on this guy. So now you made the drain to drain contact between the NMOS and the PMOS. Okay. Now the next thing to do is the VDD and ground. Similarly, just go click here. That is your VDD. Click this and this. That's your ground. And in general, usually VDD and grounds will be rails. So I would like you to just extend it like this on both sides and bring it down where you do not see this error. 2.5 is the error. So just place it on top, which is 3, right? That is your minimum spacing. And do the same here too. Okay, done. So now the next job is to perform naming, right? So in your schematic, if you remember, this was exported as, I mean, you set this as set spice model for both PMOS and NMOS. And similarly, these ports were exported. Okay, but in the schematic, we did not export the VD and ground, but in the layout, we have to export all the components. So let's just perform this. Let's export all the pins, right? Also, note in the layout, right? Whenever you want to export, if you click on this rectangular bar like this, okay, and then you do Control plus E, right? That is one way of doing it, but you would always like to go and click on this node, right? I mean, let's say you can see there is this rectangular ending. It is better you always click on this guy and then do Control plus E. Okay, so I'm going to call this as power and VDD. These are the names. These are the generic names for VDD and ground. And ground and GND. Okay. This is going to be named as, what have I named it here? Out, right? So let me name it as out. Control plus E, output, calling it OUT. Or you could also do this, wherein you just bring this, out like this and then call it out. Okay, so before, yeah, let me just call it as Control plus E, OUT. Okay. And yeah, I think I have not connected my gates together, right? That's one connection that's left out. So let me just go ahead and do that. How do I do that? In this, so always remember, whenever you have metal connections like this, right? Whenever you have two metals connecting each other, the resistance between between these 2 points is lesser than opposed to, let's say you have a polysilicon running. So in this case, I have my gates which are connected using polysilicon this way, and I'm going to bring it out also using polysilicon like this. Okay, let me do it again. Just go left click here and come near this and right click. You have a polysilicon connection. Now let's say I bring it out like this. Okay, so having lots of poly uh, being dragged out like this is not a very good idea, right? So the best way to do it is minimize how much the length of any polysilicon connections in your layout. Okay, so what I would do is, this connection is unavoidable, right? I need to connect both of these guys, so I need to have a polysilicon connection. The next step is, let's say I want to export this as a gate, right? So I have a metal 1 to polysilicon contact here. So a contact is nothing but it's like it helps you connect one type of a component with another. Like let's say in this case, it helps you connect metal 1 with polysilicon, and hence it's called as metal 1 to polysilicon contact. Okay. And there is an error here, but once you connect it, this. So to avoid these kinds of huge connections, right? So always click on the lower width guy, then click on this. Now you place it close. So now you've minimized the polysilicon distance, and let's say you want to bring this out. So what you do, you go and select metal 1 and click on this guy, bring it out like here, like this. And now export it as Control plus E, INP. Okay. Yeah. So now let's just verify if these the connections that we've performed satisfy DRC. Okay. So DRC here. So running DRC, no errors, 0 errors and 0 warnings found. So hence this layout does not have any DRC errors. Whenever there's an DRC error, we need to find out what that error is and try to correct it. Okay. Now let's look at LVS. So LVS is nothing but layout versus schematic, which is it compares every single connection made in your schematic with that of the layout and sees if the connections are all fine. Okay, before doing LVS, let me just ensure that the names, the spice models of the NMOS and PMOS are set. So again, the shortcut is Shift plus S, and you have the spice model here. Left click, and so let's say you're not able to select something, just perform Control plus left click until you see this X kind of a thing, and you again perform left click and only the X is visible. Okay, now here in the selected text, you can also see spice model. Okay, so that's the text. So that's how you select it and just bring it outside. And you can see that it's connected to this, and just name it PMOS. And do the same over here. Shift plus X. And name it NMOS. Okay, so now that I've done all the connections, so now I hope that the NCC that, so here in electric LVS, layout versus schematic, is called NCC. Okay, in NCC, go to the first option, schematic and layout views of cells in current window. So do this, you can see this value where it says hierarchical NCC is topologies match, sizes, so exports match, topology match. So this is the confirmation message that says there is no layout versus schematic errors. All the connections are done correctly. Okay, but in electric, the sizes, basically the MOSFET sizes are not checked in general. So don't worry about that. Just make sure that the sizes in your layout and the schematic are the same. So how do you do that? So just go on this guy and say Control I. Here the width is 3, the length is 2. Okay. Let's see in the schematic, the width is 2 and the length is 2. So sizes are different, but it did not show an LVS error. But just make sure that this is the same as that of the layout. Yeah, So I want PMOS, I mean an inverter which has strength 1x and 1x, that is PMOS and NMOS are both 1x itself. So I'm just going to make it 3. 3 always means 3 lambda, right? As we discussed before. And length is 2, which is 2 lambda. Control plus I, this is also 3 lambda and 2 lambda. Okay. And save it. Control plus S. Go back
We
here.
can change it, the width and length, we can change it here also, right? In the layout also, we can change it.
You can change it, but always you should ensure that the width of what I mean, you are trying to replicate whatever you've done in the schematic onto the layout. So just make sure that whatever is there in schematic is the same as that of the layout.
So
Okay.
suppose if you want width as 8 lambda and width like PMOS as 8 lambda and NMOS as 4 lambda, then we change it here and then change it in schematic.
Exactly. Just make sure in both places it's the same. Okay. Yeah. So let me just confirm that both my DRC and LVS are clear. So I'm going to rerun it and show you that DRC is clear with no errors or warnings, and tools NCC LVS, and LVS is clear with exports match, topologies match. Okay. So this is your DRC and LVS for your inverter. Further, if you want to check if the functionality of this inverter that you've designed and layout is working fine, right? So what you do is basically bring the spice code from here, Control C, and place it over here, Control V. Okay, so before running this layout spice code, let me just run the schematic spice code and show you this. So if you run the schematic spice code, all that you can see is this is basically the netlist file, right? This is your netlist and this is your spice command that runs your netlist. Okay. Here you can see that there are only 2 connections where an NMOS is connected with such and such configuration and the PMOS is connected like this and so on, right? These are the only 2 connections that you can see when you run it from the schematic. But let's say you run it from the layout. I say tools. I mean, how do you run something from the layout? You just go to double click on the layout. You will see this window. You have your spice code here. Then you go to tools, simulation spice, write spice tech. Here you're running it from the layout. Now you can see there is a bunch of different commands. I mean, the netlist file is a little more complicated than before, right? So why is this so? Because in the layout, there are some parasitics, resistors and capacitors. All of those parasitics are being written out as a netlist file. Okay. The ideal thing is that you have as minimum R's and C's from the layout such that it matches the schematic simulation as much as possible. Okay. So this is your netlist that you got from your layout. And let's just simulate this. To simulate, just click on this run. Okay, and add traces, V in and V out. So here you can see that you've obtained the result as expected. Okay, so here is your layout extracted simulation 2. And one last thing, let's say you want to comment out, let's say you don't want these spice codes inside your layout. The easiest thing is to comment it out. The comment is nothing but star. Just place star in front of everything, every line of the code, and it means it's commented out. Save it. Okay, yeah. So this is your basic introduction to inverter schematic and its layout, exporting it and running the netlist using a spice command. Okay. So I will also be sharing a little more detailed video of these other layers and other things so that you can watch that offline and clarify or like understand it in much more depth. Okay. So apart from that, if you have any doubts, you can ask me now.
So please tell again the third line of spice code.
Okay. Yeah, correct. So let's say let's look at. Let me uncomment it and run it for you again. Okay. Apply. Okay. So W plus S, I'm running it here, and add traces, V in and V out. So here you can see, let's say first I don't want V out also. Remove that. Click on this guy and delete to remove. You will see this cut kind of thing and just remove it off. Okay, so here, what is VINP, right? I have defined VINP as a PWL. Okay, uh, of and basically what it is this. So it is always you are trying to define a wave here with time instants and voltages at that instant. Okay, so at 0 seconds, you're saying that the voltage is 0 volts. That is over here. And at 100 picoseconds, you're saying that the voltage is 0.8 volts. That is here. Whenever you don't define anything between two time instants, it will just construct a straight line between those two time instants. Okay. And let's say at 1 nanosecond, it is 0.8 volt. So you can see at 1 nanosecond, again, it's 0.8 volts. So I've defined it as 0.8 volts here. It starts from here. When you define it as again 0.8 volts, it will just join these two lines. So the voltage here is a constant of 0.8 volts. And then at 1.1 nanoseconds, it is defined as 0. Until 2 nanoseconds, it's 0. So this whole line, it's 0. So it falls down from 1 to 1.1 nanosecond with a slope of whatever, right? With this particular slope.
Sir, to get the voltage transfer characteristics, we only need to do the DC run.
No, I am trying to actually perform. I'm trying to show you the inverter characteristics when you give a 1 to the inverter, right? I mean, you can also perform DC simulations where you just give a 1 here and see whether you're getting a 0, or you give a 0 here and obtain. I mean, see whether you're getting a 1.
We can change input from 0 to VDD and check the voltage transfer characteristics.
Yes, that's also one way of doing it. Yes, you can do that.
Okay.
Okay, but you will be using this transient simulations very often from next time, so you better get used to it right now.
Yes, okay.
Sir, but
Okay.
changing
Looks
the
like
input
we
from
are
0 to 1 means we need to perform transient, right?
I didn't get you. What?
So like suppose we need to just check whether the inverter is working fine, then we need to use a transient analysis, right? Like by
No,
changing
you
the
can
voltages.
also perform this transient sweep like we did in demo in the first demo session. I showed you this transient sweep, right? Yeah, here I showed you that you can actually sweep DC from one voltage to another with 0.01 volts of step. You can do this also here. You can basically step the
Okay.
yeah.
Yes, sir. Okay. Like we
Okay, you
can
can
step it
step
from
the input
0 to 1 or from
yeah 0
1
to
to 0,
0.8
something
volts
like
with whatever with some step size.
that. Okay, yes.
Sir, while performing this layout, what if one metal wire has to cross another metal wire?
So I think I did not cover this part. So whenever you say a layout, it is always in the top view, right? So you do not see the height dimension. Okay, so what these metals are is basically each of these metals are in a different height. So if you say metal 2 and you draw it on top of this guy, you bring a metal 2 and let's say I draw it here. I just connect this and then I draw a metal 2 all over like this. Okay, it means that this metal 2 is on top of metal 1. It does not cut through or anything into metal 1. So it is at a different altitude. So if you imagine in 3D, the height dimension is not shown here. So in 3D, all of these metal layers are at different y-dimensional height, if I may, or z-dimensional height. You understand
So
the
we
point?
have 2 to 3 kinds of metal wires.
Yeah. We have
this-
around we have 6 kinds of metals, metal 1 to metal 6, which all of these metals are at different altitudes or different heights.
Okay, thank you.
So Balaji, I think we are out of time now. Okay.
Okay.
So we'll share the other videos as well, right? And let them see, and we'll also share that package that they can install to see the 3D view. Okay.
Yeah. Okay.
Yeah. Okay. So they can move it around and see the actual 3D view of that circuit that they have made.
Correct,
so that will help
correct.
help them understand these things better. Okay. So we'll essentially we'll close for now. Okay. And we'll continue this discussion maybe in over the discussion forum or after you have watched a couple of more videos and also you have tried this on your own on electric. Okay.
But as far as the tutorial is concerned, I think it's done, right? We've
that is done. That's all. Yeah. So we have not spoken about the body connection, but that we'll do later. Yeah.
Okay.
Yeah.
Thank you.
Yeah. Somebody had a question.
Sir, actually, I wanted to ask a general question. Like, sir, will we have class on this Friday? As in the last class, we came to know that Friday is an institute holiday, so that's why.
No, then we'll have it on Thursday.
Okay, sir.
Yeah, we'll have it on Thursday this time. Yeah. Okay.
So I'm sorry, we'll have class on Thursday instead of Friday.
Yes. If it's an institute holiday, then it will be on. I'll have class on Thursday, the live session discussion.
Oh, okay, sir. Oh, okay. This Friday is institute holiday, is it?
Yeah. Yes.
Okay, sir. Yeah.
Okay. Yeah. Okay. Right. Okay. Then thank you all. We'll meet on Thursday.